In this video, we're going to be working with surface integrals. Let's start with some notation. We'll say that d little s is the element of arc length. And we'll say d capital S is the element of surface area. So visually what these represent, in the first case, if we've got a curve, ds represents just a tiny bit of length along that curve, so tiny bit of arc length. Whereas d capital S applies when we've got some sort of surface. Let's say we've got maybe a paraboloid, and our d capital S would represent a tiny little chunk of surface area on that surface. When we're working with surface integrals, it's this d capital S that we're going to be seeing. And because we've got these two pieces of notation that are quite similar, when I write the capital S, I try to make it look like a script S so that we can easily understand that that's d capital S, meaning our element of surface area. So let's define what a surface integral is. It's going to be a double integral over our surface of some function times d capital S. So what this calculates geometrically, calculates an infinite sum of quantities that look like f times d capital S, where this infinite sum is over infinitely many tiny areas d capital S. So a surface integral is breaking our surface up into infinitely many of these infinitesimal areas ds, calculating the value of f in each little area, multiplying that by the area itself, and then summing up those quantities. Let's do a quick example to see what we can use surface integrals for. So we've already seen in an earlier video how to calculate surface area for a surface. So we call that SA. That's just going to be the double integral over our surface of d capital S. We could also calculate the mass of our surface. We could say mass is the double integral over S of the density times d capital S. We could talk about the centroid of our surface. So in notation, we would call that x bar, y bar, z bar. And for example, if we wanted x bar, we would say that's 1 over the mass of our surface times the double integral over our surface of x delta d capital S. We could also calculate the moment of inertia with respect to any of our three axes. So for example, if we wanted to go with respect to the z-axis, we could say I sub z is going to be the double integral over our surface of x squared plus y squared times our density times d capital S. So these are the same integrands that we use for double integrals, for triple integrals, and also for line integrals. We're now just seeing these same formulas in the context of surface integrals. So let's recall that there are two ways to calculate d capital S, and we're going to remember these, recall these here so that we can jump into some calculations. If you want more context for this, I would suggest that you look back at the video called Surface Area, where we talked about these two formulas in more detail. So let's recap them here. The two situations we want to think about. First situation is if z is an explicit function of x and y. Let's say z equals h of xy. We have one formula for d capital S. And the other situation is if our surface S is parametrized by two parameters, let's call them u and v. So then we'll have a second formula for d capital S. So in the first situation where z is an explicit function of x and y, then d capital S looks like a certain square root times dy dx. And under the root, we have 1 plus the partial of z with respect to x squared plus the square of partial of z with respect to y. In the other situation where we have a parametric surface, let's say our parameters are called u and v. Well, in this context, we would be given a position vector for all the points on the surface. We call that position vector vector r. So the way that we would calculate d capital S is we would take the partial of r with respect to parameter u, and then we do the cross product of the partial of r with respect to v. Take the length of that vector and then multiply that by du dv. And that gives us our d capital S for a parametric surface. So let's evaluate the surface integral, double integral over our surface of z squared ds, where our surface S is the first octant of the unit sphere centered at the origin. So if we like, we could just draw a rough picture for ourselves, going 1 unit out in all of these directions here. And we're just interested in the portion of this surface where x, y, and z are all positive. So there's our surface S. So first thing we could do here is take the formula for our surface and let's solve that for z. So we could say z squared equals 1 minus x squared minus y squared. That means z is either plus or minus the root of 1 minus x squared minus y squared. If we wanted the upper hemisphere, we would use the positive root and we'd use the negative root for the lower hemisphere. Since we know from our picture that we want our z coordinates to be positive, we're going to choose the positive root. So now we're going to work towards calculating d capital S, and to do that we need to find our partial derivatives. So we need z sub x and z sub y. Let's work on z sub x first. Well, according to the chain rule, it will look like 1/2 1 minus x squared minus y squared, now to the power minus 1/2, and then times the partial derivative of the inside function with respect to x. So that'll be minus 2x. And if we rewrite that a little more neatly, that's going to look like minus x over the root 1 minus x squared minus y squared. Now, if we went through the same kind of reasoning for z sub y, we would find z sub y is going to be minus y over that same root. So we know from our previous discussion, d capital S is going to be the square root of 1 plus the sum of the squares of our partial derivatives, and then that's times dy dx. So let's plug in here and see if we can simplify what's happening under the root. So under the root, we've got 1 plus, we've got the square of our z sub x, so that's going to look like x squared over 1 minus x squared minus y squared, and then the square of z sub y is going to look like y squared over 1 minus x squared minus y squared. And that whole root is still times dy dx. So in order to simplify this, let's create a common denominator under the root. Let's think of that 1 as being 1 minus x squared minus y squared over 1 minus x squared minus y squared. And that way we can put everything under that root just over a common denominator. So under this root, everything's now over this 1 minus x squared minus y squared, and our numerators, 1 minus x squared minus y squared plus x squared plus y squared, that just becomes 1. So then we could pass that root to the numerator and the denominator. So we'd have on top root 1, which is just 1, and on the bottom root 1 minus x squared minus y squared. And that's times dy dx. So that now gives us a simplified version of d capital S, and that's what we're going to need to plug into our double integral to actually compute it. Now, just to avoid a little bit of writing here, let's notice that this root that we're seeing in the denominator is actually an expression that we've seen earlier in this problem. Remember, we said up here, z is that square root of 1 minus x squared minus y squared. So if we wanted to do the minimum amount of writing here, we could actually say this is 1 over z times dy dx. And when we go over to our surface integral, it's going to be nice to have that written down concisely. So here's what we're trying to evaluate. We're doing the double integral over our surface of z squared d capital S. And let's start to plug in here. So the idea is that we're moving over to the new variables x and y. So when we write down our double integral now, I'm going to write r, which is going to be a region of the xy plane. We'll draw a picture of that in a minute. We've got this z squared, which gets multiplied by d capital S, which is 1 over z dy dx. So let's look at this integrand for a second here. Definitely there's a factor of z that can cancel out from the top and the bottom, so we could just call that z. But even better, we could re-express that z in the language of x and y so that we can actually do our integration. So that z is 1 minus x squared minus y squared all square rooted. And that way now we've got a double integral that we can evaluate. So let's think about what this region R represents. It's the region of the xy plane that you want to do your integration over. And if we think about our picture, remember our surface was a unit sphere centered at the origin, and we just wanted the first octant of that. So in our picture, R is this region of the xy plane that we want to do our integration over. And if we just focus in on the xy plane and think about what that looks like, well, that's a quarter circle in the first quadrant, where that quarter circle has radius 1. So the best way to describe this region then is going to be in polar coordinates. Let's say our region R, radius values will range between 0 and 1. And because we're just doing the quarter circle, because we just want to capture the x and y values that are positive, we'll just use angles theta between 0 and pi over 2. So now that we've decided polar coordinates are the way to go, let's convert this entire integral here over into polar. So our integrand is going to become root 1 minus r squared when we move into polar. That's because x squared plus y squared is equal to r squared in polar. Our dA here, the dy dx, becomes r dr d theta when we convert into polar. Remember, there's always that correction factor of r when we move from rectangular to polar. And then we can put our limits of integration on there. So 0 to 1 and 0 to pi over 2. Okay, and then let's get on to the actual double integration portion of the calculation, and we'll come up with our numerical value for our surface integral. So looking at this inside integral, we may want to do a substitution here. I'll just show the details on the side if you do want to see all the details for that. So the integral we're trying to compute is the integral 1 minus r squared times r dr. We would sub u equal 1 minus r squared. du would become minus 2r dr, which means minus 1/2 du is the same thing as r dr. So if we look at the integral that we're trying to compute here, rephrase that in terms of u, that's minus 1/2 integral root u du, which gives us minus 1/2 times, integrating the root u, we'd have u to the 3/2 times 2/3 plus a constant. So overall minus 1/3 times 1 minus r squared to the power 3/2 plus a constant. So there's our substitution in all its glory. Typically you just do that part over on the side, and then we can come back to our double integral and finish our computation. So I'm going to continue the computation over here. Okay, we'd still have our integral with respect to theta on there. We've figured out how to evaluate that inside integral there, so that's going to give us minus 1/3, 1 minus r squared to the power 3/2, and that's going to get evaluated at r equal 1 and r equals 0. I think it would be easier if I brought that minus 1/3 out in front. Okay, and then we can evaluate. We've got minus 1/3 times the integral from 0 to pi over 2 d theta, and then evaluating at r equal 1 we get 0, and at r equals 0 we get minus 1. So that's looking good. Bringing all our constants out in front then, we've got 1/3 now, positive 1/3, times the integral from 0 to pi over 2 d theta, and this part here is just going to give us pi over 2. So for our final answer, for our surface integral, pi over 6. So two key aspects of the problem that we concentrated on here. First was the actual calculation of ds, which we did around here. So because z was an explicit function of x and y, we were able to use this formula to calculate ds. And then once we had that, then we needed to change our surface integral all over into the language of x and y. And that's where you think about the region R of the xy plane that you're integrating over. We're going to try a second example of a surface integral, doing the double integral over our surface of y plus z times d capital S, where our surface S is given by the following position vector. So we've got a parametric surface. The values of a and b would be given in this type of context. A is ranging from 0 to 2 and b is ranging from 0 to pi over 2. So let's draw a quick picture of our parametric surface just to get a visual on what we're doing here. I would say let's look at what's happening in the xz plane. So look at the x coordinates and the z coordinate of your position vector and think about what's going to happen as b ranges from 0 to pi over 2. So when b equals 0, our x coordinate is 3 and our z coordinate is 0, so we're there. And then at b value pi over 2, our x coordinate here becomes 0, our z coordinate becomes 3, so we're up at this point here. So what's happening in the xz plane is we're getting this quarter circle here, radius 3, centered at the origin. And while that's happening, let's think about what's going on with the y values. So the y values are ranging between 0 and 2. So as we let a range between 0 and 2, and we let b range between 0 and pi over 2, what we're getting is this sort of a shape. So that's our two-dimensional surface S in 3D. I would say the drawing is not strictly necessary here, but it's just to give us a visual of what's happening. So the surface integral we're interested in computing here, we're going to be integrating over our surface the function y plus z. So to get going with this, we're going to calculate d capital S. And to do that for a parametric surface, you want to take the partial derivative of your position vector with respect to your two parameters. So if your parameters were called u and v, you'd write vector r sub u and vector r sub v. In this case, for whatever reason, our parameters are called a and b. All right, so let's take those two partial derivatives. Partial of r with respect to a is going to be 0, 1, 0, and partial of r with respect to b, minus 3 sine b, 0, and 3 cos b. So next thing we want to do is take the cross product of these two vectors that we've just calculated. So we'll write down our 3 by 3 determinant with ijk in the first row. Then we've got our 0, 1, 0, our minus 3 sine b, 0, 3 cos b, and we'll just figure out this 3 by 3 determinant. So expanding along the top row, we'd have I times 3 cos b. Remember, there's always the sign change for the j term, so minus j times, well, that's going to be 0, and then plus k times 3 sine b, because we're going 0 minus a negative 3 sine b gives us a plus 3 sine b. Okay, so if we write that back into component notation, our cross product looks like 3 cos b, 0, 3 sine b. So now what we'd like to do is take the length of this vector, and if we multiply that length times dA dB, that's giving us the d capital S that we're looking for. So let's get that part done. So length of our cross product is going to be square root sum of the squares of our different components. So under the root, we'll have 9 cos squared b plus 9 sine squared b. That's still times dA dB. And under that root, we could just factor out that 9 there. So under the root, we've got 9 times cos squared b plus sine squared b. That part there is just going to give us 1. So this is like root 9, in other words, 3 times dA dB. Great, so we've got d capital S now written in the language of a and b, and that means we're ready to go back to our surface integral and just rewrite everything in terms of a and b. So let's scroll back to the problem here just so we can see the surface integral that we're trying to compute. There it is. So let's copy that down here and continue with our calculation. So we want the surface integral over S of y plus z, d capital S, and let's start to write everything in terms of a and b. So we'll have a double integral of some integrand, and then our ds is going to be 3 times dA dB, so we might as well write that 3 add in front of the integral. And let's think about our integrand. So we want to integrate y plus z, but we want y plus z written in the language of a and b. So to do this, let's look back at our position vector, which we're given in the question. And we've got formulas here for what does x look like, what does y look like, what does z look like in the language of a and b. So y is going to be a and z is going to be 3 sine b. Okay, so that's exactly what we'll use here to rewrite our integrand. So that's going to be a plus 3 sine b. And then the last thing that we need here, limits of integration. Those were also given in the problem. So if, for a parametric surface, you'd be given the range of a and b values. A is ranging from 0 to 2, b is going from 0 to pi over 2. So let's plug those in there as well. And then we're ready to proceed with our integration. So let's do our integration with respect to a. We'd have a squared over 2 plus 3a sine b, and we're going to evaluate that at a equal 2 and then a equals 0. So we'll keep our constant on there, keep our integral with respect to b on there, and then just evaluating, we'd have 2 plus 6 sine b. And then evaluating at a equals 0 gives us 0. So no new terms coming in there. So now we just need to do our last integration with respect to b. So we'd have 3 times, while integrating with respect to b, 2b minus 6 cos b. And then let's evaluate that at b equal pi over 2 and b equals 0. So at b equal pi over 2, that would give us pi. Cos term is 0 at pi over 2. So we don't need to write that down. And then subtracting off the value at b equals 0, we'd have minus 0. And let's evaluate this minus 6 cos b at 0. So that would give us a negative 6. So we're going minus negative 6 there to get that done. So that's looking like 3 times pi plus 6. So we could leave our answer like that, or we could say 3 pi plus 18. So that's the value of our surface integral for a parametric surface. Thanks for watching.